Alright, time to do some more discussion about the way we represent compounds in a fashion that we call electron dot structures. These are all based on what we know as Lewis structures. The Lewis structures are derived by a fellow named Lewis, as you might imagine, and they represent the atom's valence electrons using dots distributed around the symbol for the atom, no more than 8 dots around any one atom representing the valence electrons. These indicate in a general sense how the valence electrons are going to be distributed in a molecule. So you can see from this simple cartoonish diagram that as you go across a period you add one more dot, and each element has dots arranged singly before you add a pair of them on any one side. And it gives us an idea about how electrons are going to form be shared in bonds, because this is how we use them for non-metals making covalent bonds. So the way Lewis proposed it is atoms are going to share electrons in order to have a more stable electron configuration such as that of a noble gas. And so hydrogen, when it shares with its neighbor, is going to end up with 2 electrons, which is like helium. When fluorine makes a molecule, it's going to end up with a total of 8 electrons like neon, and so forth. We'll see more examples in more detail here gradually. As is famed in some cases, the back of an envelope or a restaurant napkin is sometimes the places that ideas in science are worked out in unusual locations. So whatever the case, we still need to remember an octet, because when we're making covalent bonds, there's going to be an octet of electrons around a particular atom. How does that work? Let's look at some examples. Okay, so these Lewis structures will be for things as simple as hydrogen. That's the simplest possibility, apparently. And each hydrogen has 1 electron represented by a dot. If you bring the 2 hydrogen atoms together to make a hydrogen molecule, well, now you have 2 electrons. Between the 2, there's shared electrons. The shared electrons constitutes a covalent bond. And so from the diagram at the lower portion of the screen here, you see that you have a shared pair between the 2 atoms, and the hydrogen atom on the left will have be experiencing or have 2 electrons circulating about it, and the hydrogen atom on the right also has 2. Each of them then has a full valence shell equivalent to that of helium. We can go beyond hydrogen to something a little more complicated. So fluorine molecules are formed from 2 fluorine atoms, which have normally 7 valence electrons, and they're shown with black and red dots here. The black dots indicate the ones that are not ending up to be shared, and the red ones that are shared. So between the 2, you end up with a bonding pair that is holding them together as a covalent bond, and the rest of the black dots around the fluorine atoms are described as lone pairs. They are not bonding pairs. And so the result is that each fluorine atom is surrounded by 8 valence electrons. And if we think about this carefully, the bonding pairs in between, the lone pairs on the side, and we can loop around each fluorine atom to represent the fact that there's 8 electrons below. Around each fluorine atom, essentially the same as a full outer shell. The molecules of oxygen and nitrogen, which are also diatomic, are somewhat more complicated, because oxygen, having 6 valence electrons, will have to do more than share 1 pair of electrons to end up with an octet. And so when oxygen forms an O2 molecule, the atom on the left has to share 2 pairs of electrons with the atom on the right, but in so doing, each of them has an octet, and in this case it's a double bond, unlike the fluorine and hydrogen examples. With nitrogen, it has 1 lone pair of its 5 valence electrons and 3 unpaired electrons. To put them together in a fashion that makes an octet, the only way that works is to make a triple bond. So you can think of all 8 of those electrons circulating around the left nitrogen atom, and the 3 pairs in the middle plus 1 lone pair circulating around the right nitrogen atom to make another octet. So each nitrogen atom experiences an octet, a stable octet around it, but they're sharing 3 pairs in the triple bond. So let's look at some examples of simple compounds for group 3A which begins with boron. Remember, this is going to be nonmetal, so we aren't really going to discuss group 1 and 2A elements in covalent bonds. So group 3A elements have 3 valence electrons, just the way we've learned that group number corresponds to the number of valence electrons. And this is an odd one because these are actually only going to form 3 electron pairs, namely bonds. We call them bonds. And the simple example here is with hydrogen and boron in a compound that's called borane, or boron tetrahydride, or trihydride, trihydride. And in this case, 1 hydrogen electron in each bond and 1 boron electron in each bond still ends up with only 6 electrons. So boron is odd, and boron is one of these odd notable exceptions that doesn't reach an octet. But the remainder of our examples in the rest of this discussion essentially will. So group 4A elements, so what's next to boron would be carbon, things like carbon, and anything in group 4A in general sense has 4 valence electrons, just like the group number, and that means you're going to look to form 3 electron pairs, aka bonds. 4 bonding pairs makes an octet. So if you put carbon with 4 hydrogens, a simple compound there, then you will have an octet around the carbon. And the hydrogen atoms, again, should not have an octet because they're only going to make a full shell like their nearest noble gas neighbor, and that would be helium with 2. So each hydrogen atom is never going to have more than a single bond, and or described as only a pair of electrons being shared with its neighboring atom. That's what we're looking to expect. So, progressing onward. That one has a name. It's called methane, aka natural gas. Group 5A elements. So, as we've noted the pattern, group 5A elements should have 5 valence electrons distributed with 3 singles in 1 lone pair, as is typical with nitrogen. And those 3 singles are going to make 3 electron pairs, namely we call them bonds. And so if you combine it with hydrogen, we have what's known as NH3 or ammonia. And in this case, the nitrogen has shared electrons from 3 neighboring hydrogen atoms to end up with an octet. And again, the hydrogen atoms each have only 2 electrons to fill their outer shell, which is a stable arrangement. Again, it's not 8 because it's hydrogen. You can't go that high with electrons. And so that makes a stable configuration of 3 bonds and then 1 lone pair or ammonia. If you go beyond group 5A, group 6A with 6 valence electrons, well, the easiest simple group 6A element would be oxygen. Combine that again with hydrogen, and you have water. Well, so what are we going to do? We have 2 lone electrons and 2 lone pairs of electrons. And so the 2 singles, as it were, are going to create bonds with each hydrogen. And so the result is that you get an octet by having 2 bonds and 2 lone pairs around the oxygen, and the hydrogens still get just 1 bond, what can be called a duet, but normally we just talk about 1 bond for hydrogen, and that's a stable configuration like a nearest noble gas. So group 6A followed by 7A. So as the pattern continues, we're expecting 7 valence electrons, but now we have 3 lone pairs and 1 unpaired electron. So the 1 unpaired electron is the one that makes a bond. In this case, we make a compound with hydrogen. We call it hydrogen fluoride. The hydrogen is going to have a duet of 2, and the fluorine is going to have an octet of 8, a stable arrangement. But again, it's 1 bond and 3 lone pairs that results in that configuration for fluorine. So group 7A is followed by group 8A. Well, what do we know about those? Well, group 8A is the noble gases, and they have 8 valence electrons, and in a general sense, they seldom form electron pairs. They've already got octets. There's no tendency for them to form bonds unless we're doing unusually extreme conditions for compounds with xenon and fluorine, for example. So we won't generalize those too often, but now and then you'll see some representations of their structures. So in a general sense, think of not forming bonds with noble gases. So one other way to remember how these structures work is that the number of valence electrons gives us a way to know how many bonds are formed, and these are particularly helpful when you realize where they sit in the periodic table. So group 3A is a little odd because boron doesn't make an octet, but from group 4 across to group 8, the number of bonds formed is going to decrease because it corresponds to the number of valence electrons having and what's remaining to fill it up to 8. So if you add 4 plus 4 for carbon or group 4 members, you get 8, and 5 plus 3 for group 5 elements, you will get 8. 6 plus 2 more is in bonds, shared from somewhere else, ends up with 8 for group 6, and so on. So use that pattern, but remember that boron is an oddball, and it's not likely going to make any bonds. Or it's not going to make an octet. Sorry, I said that incorrectly. All right, so just to recall, I looked at earlier, a few slides back, structures of O2 and N2, these diatomic molecules. And there's another thing we can describe in looking at these structures. When you form a double bond or a triple bond, we have now a new term to describe. The double bond and triple bond are described as having bond orders of something greater than 1. A bond order of 2 is what you get with a double bond. And when it's a bond order of 3, that's for a triple bond. So now and then we will discuss bond order, and it simply relates to the numbers of bonds between the atoms. Another thing to note about these structures and the resulting physical properties is that these multiple bonds are going to form from time to time. An example with O2 here, or N2, we just mentioned double and triple bonds. And if you have a double bond between two oxygens, its bond length is going to be much shorter, as it turns out, than a single bond. Likewise, the triple bond between two nitrogens in N2 is much shorter than a single bond. In this other compound, N2H4, it has a name, it's called hydrazine. But they're shorter and much stronger when they're multiple bonds. So in other words, the double bond is going to take more energy to break than its neighboring single, or its similar single bond in between two oxygens. Or the triple bond between two nitrogens is going to be a lot more strong, a lot more energy to break it than the single bond between two nitrogens. That just concludes my conversation about the electron dot structures for this section. I hope it's helpful to you as you work on your assignment.